In December 2022, when Northrop Grumman unveiled the B-21 Raider at Plant 42 in Palmdale, California, the world glimpsed what appeared to be a smaller, sleeker version of the legendary B-2 Spirit. Defense analysts immediately began comparing wingspan measurements and speculating about range, but they were witnessing something far more revolutionary than they realized. Air Force officials have carefully hinted at capabilities that go far beyond traditional radar stealth, suggesting this bomber incorporates technologies designed to counter the most sophisticated detection systems that nations like China and Russia have spent billions developing, including advanced space-based sensors. How has Northrop Grumman approached the challenge of evading satellite detection? Join us as we explore how the B-21 Raider's revolutionary stealth technology is redefining what's possible in modern warfare and challenging adversaries' most advanced detection capabilities. The challenge of defeating space-based sensors is one of the most difficult problems in modern stealth technology. Ground-based radars can be evaded by flying low, using terrain masking, or simply staying outside their range. Infrared search and track systems on ships or aircraft have limited detection ranges and narrow fields of view. But space-based infrared satellites orbiting in geosynchronous or highly elliptical orbits maintain continuous surveillance of vast areas, imaging the Earth's entire surface every 10 seconds, while searching for infrared activity indicating heat signatures. The United States operates the Space-Based Infrared System, or SBIRS, a constellation of satellites equipped with shortwave and midwave infrared sensors, capable of detecting any significant thermal event on the globe, from ballistic missile launches to aircraft engine exhausts to explosions and fires. These sensors were designed primarily for missile defense, providing early warning of ICBM launches by detecting the enormous infrared signature of rocket motors during the boost phase. However, SBIRS and similar systems operated by Russia and China can also potentially detect aircraft, particularly large bombers with powerful engines generating substantial heat. Traditional stealth technology focused primarily on defeating radar through careful shaping and radar-absorbing materials. The F-117 Nighthawk, America's first operational stealth aircraft, used faceted surfaces that reflected radar waves away from transmitters, making it extraordinarily difficult for enemy radars to detect. The B-2 Spirit advanced this concept with smooth curves and a flying wing design that minimized radar returns, while also incorporating measures to reduce infrared signature, including shielding engine exhaust and using special coatings. However, both aircraft still produced detectable heat signatures that sophisticated infrared sensors could potentially track, especially during takeoff and landing when engines operate at maximum power. Space-based infrared systems, looking down from orbit with unobstructed views and able to integrate observations over time, posed a growing threat that designers needed to address with new approaches. The B-21 design team, working 3 decades after the B-2 with access to revolutionary materials science, advanced computational modeling, and a deep understanding of adversary sensor capabilities, approached the infrared challenge with completely new technologies. Rather than simply trying to minimize heat signature, they engineered the aircraft to control and manage its thermal emissions across multiple infrared bands simultaneously. This multispectral approach recognizes that space-based sensors operate across different wavelength ranges, each optimized for detecting specific types of thermal activity. Shortwave infrared excels at detecting very hot objects, such as rocket exhaust plumes. Midwave infrared provides balanced sensitivity for tracking aircraft engine heat. Long-wave infrared detects cooler objects and is less affected by atmospheric absorption. An aircraft designed to counter these threats must manage its signature across all these bands simultaneously, an extraordinarily complex engineering challenge. Northrop Grumman has developed advanced materials and coatings that interact with infrared energy in sophisticated ways, though the exact specifications remain highly classified. Unclassified research into infrared stealth technologies provides hints about the underlying principles. Advanced coatings can be engineered to absorb, reflect, or emit infrared radiation at specific wavelengths in a controlled manner. The aircraft's skin might be designed to dissipate heat in wavelength bands where atmospheric water vapor and carbon dioxide absorb the energy before it reaches orbital sensors, while suppressing radiation in bands where satellites are most sensitive. These technologies represent a significant advancement over earlier stealth materials, though their exact effectiveness against space-based detection remains a closely guarded secret. The engine integration represents one of the most impressive visible aspects of B-21 design. Traditional bombers like the B-52 have engines mounted in pods beneath the wings or fuselage, fully exposed to observation from any angle. The B-2 buried its engines deep within the wing structure and exhausted them through slots on the upper rear surface, shielding the hot exhaust from ground-based infrared sensors. The B-21 advances this concept with engines so deeply integrated into the airframe that external observers can barely see the intake or exhaust openings. Reports suggest the engines are derived from the Pratt & Whitney F-135 that powers the F-35 Lightning II, but modified extensively for the bomber application with emphasis on fuel efficiency and reduced thermal signature rather than maximum thrust. The exhaust management system likely incorporates multiple technologies working in concert. Mixing cold bypass air with hot exhaust gases reduces the plume temperature before it exits the aircraft. Flattening and diffusing the exhaust stream increases its surface area, accelerating cooling through contact with ambient air. The exhaust appears to be directed over the aircraft's upper surface, using the body itself as a heat shield that blocks direct observation of the hottest portions of the plume from certain angles. These techniques combine to dramatically reduce the infrared signature compared to conventional bombers, though exactly how effective they are against satellite detection remains unclear to outside observers. The B-21's platform and size contribute to its stealth characteristics. Satellite infrared sensors detect objects by identifying bright spots against the relatively cool background of Earth's atmosphere and surface. A large, hot aircraft presents an obvious target. The B-21 is reportedly smaller and lighter than the B-2 Spirit, with an estimated wingspan of around 140 feet compared to the B-2's 172 feet. This size reduction directly decreases the thermal signature, as there's simply less airframe surface area being heated by aerodynamic friction. The flying wing design minimizes the frontal area exposed to airflow, reducing drag and the associated heating. Every surface that touches air heats up through friction, and managing this aerodynamic heating represents a key component of signature management. The operational profile further enhances stealth capabilities. While specific performance parameters remain classified, the B-21 is known to be subsonic, designed for efficiency rather than speed. This choice reflects the reality that speed no longer provides escape from modern air defense systems capable of engaging targets traveling Mach 2 or faster. Instead, low observability and unpredictability offer better survival odds. By flying at moderate speeds, the B-21 minimizes aerodynamic heating and fuel consumption, both of which help reduce thermal signature. The aircraft can potentially vary its cruising altitude and speed based on mission requirements, optimizing its flight profile to minimize detectability during critical mission phases. Digital engineering revolutionized how the B-21 achieved these capabilities. Unlike previous bombers designed using traditional methods with physical mock-ups and iterative prototyping, the B-21 was created entirely in the digital realm first. Engineers built complete virtual representations of the aircraft, incorporating every system, material, and component. They simulated how the bomber would perform aerodynamically, structurally, and thermally under countless conditions, refining the design until it met all requirements before cutting the first piece of metal. This approach allowed exploration of design options that would have been impractically expensive to test physically, enabling optimization across multiple parameters simultaneously. The digital approach also enabled unprecedented integration between disciplines. Traditional aircraft design often involves separate teams working on structures, propulsion, avionics, and stealth, with limited communication between groups until problems emerged during assembly. The B-21's digital twin allowed structural engineers to see immediately how their design decisions affected thermal signature, propulsion specialists to understand how engine placement influenced radar cross-section, and materials scientists to optimize coatings for both durability and signature reduction simultaneously. This holistic integration produced a bomber where every element serves multiple purposes, and stealth is built into the fundamental architecture rather than added as an afterthought. Remarkably, a flying testbed aircraft accumulated over 1,000 flight hours, testing production hardware, software, and sensors before the first actual B-21 ever flew. This surrogate aircraft, reportedly a modified existing platform, validated that the systems functioned as modeled and enabled the discovery and correction of issues in a lower-risk environment. When the first B-21, designated T-1, finally took to the sky on November 10, 2023, from Edwards Air Force Base in California, it represented one of the most thoroughly tested aircraft ever to make a maiden flight. The transition from design to flight testing has been extraordinarily smooth compared to previous programs, with officials consistently noting fewer unknowns and problems than expected. This success validates the digital engineering methodology and suggests the B-21's capabilities align closely with what designers intended. Testing and analysis since that first flight continue to expand the understanding of the bomber's performance. While specific test results remain classified, Air Force officials have made carefully worded statements indicating the B-21 meets or exceeds all stealth requirements across multiple threat domains. The aircraft has flown numerous test missions during both day and night, in various weather conditions, executing maneuvers and profiles that simulate operational employment. Throughout this testing, the Air Force has maintained strict information security, with most missions unannounced and details closely guarded. This operational security itself suggests confidence in the aircraft's low observability characteristics. The second test aircraft, designated T-2, joined the flight test program in September 2025 after completing extensive ground testing at Edwards. The arrival of this second Raider provided maintainers with valuable hands-on experience with tools, data, and processes that will support future operational squadrons. By early 2026, multiple test aircraft are involved in flight and ground testing, with the program expanding faster than any previous bomber development. The rapid pace reflects both the maturity of the design, thanks to digital engineering, and the urgency with which the Air Force views the need for this capability. China and Russia are fielding increasingly sophisticated air defense networks specifically designed to counter American stealth aircraft, and the aging B-2 fleet of only 20 aircraft cannot provide sufficient capacity to meet all potential contingencies. Initial operating capability is projected for the late 2020s or early 2030s, though the exact timeline remains somewhat flexible. The Air Force has suggested that deterrence roles could potentially be achieved earlier, with aircraft transitioning to operational service as testing validates their capabilities. This readiness reflects how close the test aircraft are to their final operational configuration. Historically, test aircraft were bare-bones platforms incapable of combat, requiring extensive modifications before entering service. The B-21 test birds, benefiting from comprehensive virtual testing and surrogate aircraft validation, are much closer to combat-ready condition. The strategic implications of advanced stealth technology transform the calculus of deterrence and warfighting. For decades, nations have invested in satellite constellations and advanced sensor networks specifically to counter American military advantages. China's development of sophisticated imaging satellites and advanced infrared detection systems aims to track aircraft that radar cannot see. Russia continues upgrading its sensor networks with new technologies designed to detect low observable targets. Both nations have assumed that even if stealth aircraft evade ground-based radars, space-based and other advanced sensors would provide tracking data allowing engagement. The B-21's design philosophy directly challenges these assumptions, incorporating technologies intended to counter the full spectrum of detection methods. Consider how advanced stealth capabilities could affect military operations in contested regions. Traditional mission planning would need to account for satellite coverage windows and time operations to avoid periods when infrared satellites have optimal viewing geometry. An aircraft with significantly reduced detectability across multiple sensor bands potentially has greater operational flexibility, able to conduct missions during windows based on target vulnerability, weather, and other factors, rather than being as constrained by satellite orbits. This flexibility transforms operational planning and creates uncertainty for adversaries attempting to defend high-value targets. The networking and sensor capabilities built into the B-21 add another dimension to its strategic value. Unlike the B-2, which was essentially a penetrating strike platform, the B-21 is designed as a node in a broader family of systems encompassing intelligence, surveillance, reconnaissance, command and control, and electronic warfare. The bomber carries advanced sensors that gather information about adversary air defenses, communications, and activities. It can share this intelligence with other platforms through highly secure data links, creating a common operational picture that enhances the effectiveness of the entire force. The B-21 might penetrate denied airspace not just to deliver weapons, but to map enemy defenses, identify targets for other systems, or relay communications for forces operating in contested areas. This multi-mission flexibility stems from the bomber's open architecture design philosophy. Rather than hardwiring capabilities that become obsolete as technology advances, the B-21 uses modular systems and standardized interfaces that allow rapid insertion of new capabilities. Software updates can add new tactics, integrate new weapons, or enhance sensor processing without requiring physical modifications. Hardware upgrades slot into existing spaces using standard connectors and power systems. This adaptability ensures the bomber can evolve throughout its projected 50-year service life, continuously improving faster than adversary countermeasures can be fully developed and fielded. The Air Force describes this approach as continuous capability delivery, in which improvements flow to operational aircraft at the pace of software development, rather than through decade-long acquisition programs. The weapons integration showcases this flexibility. The B-21 is confirmed to carry nuclear weapons, including the B-61 Mod 12 gravity bomb, and will eventually carry the AGM-181 long-range standoff missile. These nuclear weapons provide the strategic deterrence mission that justifies the program's highest priority status. However, the bomber will also deliver conventional weapons, including the AGM-158 JASSMER cruise missile, potentially hypersonic weapons currently under development, and a range of precision-guided munitions. The internal weapons bays reportedly accommodate large weapons without requiring external carriage that would compromise stealth. Unlike the B-2, which was designed when precision-guided weapons were relatively large and expensive, the B-21 benefits from modern miniaturized weapons that pack equivalent or greater effectiveness into smaller packages. The maintenance and sustainability improvements over the B-2 are equally significant. The B-2 Spirit's low observable coatings were notoriously difficult to maintain, requiring climate-controlled hangars and extensive work after each flight to repair degraded materials. This made the B-2 extraordinarily expensive to operate and limited its availability. Often, fewer than half the fleet were mission-ready at any given time. The B-21 employs next-generation low-observable materials engineered from the beginning for durability and easier maintenance. The coatings are designed to withstand standard airfield servicing, support multiple sorties without requiring extensive repairs, and potentially operate from forward bases without requiring specialized facilities. This sustainability transformation aims to dramatically reduce operating costs while increasing availability. Pacific Theater operations drove many B-21 design decisions, reflecting the reality that China represents the pacing threat for American military planning. The vast distances of the Indo-Pacific demand long-range and high endurance. The sophisticated air defenses China has deployed, including advanced radars, long-range surface-to-air missiles, and integrated sensor networks, require cutting-edge stealth technology. The distributed basing concepts being developed for potential conflicts in the region envision operating from various locations throughout the theater. The B-21 addresses all these requirements, representing the first American bomber designed from the beginning with these modern conflict scenarios as the primary driver. Cost control represents one of the B-21 program's impressive achievements. Northrop Grumman and the Air Force set a target average procurement unit cost of $550 million in 2010 dollars, equivalent to approximately $640 million to $700 million in current dollars. By most accounts, the program has remained relatively close to this target, a notable accomplishment for a cutting-edge military aircraft incorporating revolutionary technologies. The digital engineering approach reduced the need for costly physical prototyping and testing. Emphasis on maintainability aims to lower lifecycle costs, which account for the majority of total ownership expense. The result is an aircraft that, while expensive in absolute terms, aims to deliver extraordinary capability at a controlled cost compared to alternatives. The global response to the B-21 reflects recognition of its strategic significance. American allies operating under the nuclear umbrella or facing regional threats view the bomber as reassurance that the United States maintains technological superiority and commitment to their defense. The United Kingdom and Australia have expressed interest in potential cooperation, though export of the actual aircraft appears unlikely given the sensitivity of the technologies involved. Japan and South Korea, facing North Korean missile threats and Chinese military expansion, welcome capabilities that enhance deterrence and provide additional options should conflict erupt. Adversaries view the B-21 with concern and are working to develop countermeasures. China's investment in advanced imaging satellites, new radar technologies, and sophisticated infrared sensors specifically targets the challenge of detecting stealth aircraft. Russia continues upgrading its air defense networks with new radars and missiles designed to engage low observable targets. Both nations recognize that advanced stealth capabilities could compromise their ability to defend high-value targets. However, developing and fielding effective countermeasures requires not just theoretical understanding, but practical implementation of extraordinarily complex technologies, a challenge that takes years or decades to overcome. The B-21 program timeline continues advancing with multiple aircraft now in testing and production ramping up at Plant 42. Ellsworth Air Force Base in South Dakota will be the first operational base, with extensive military construction underway to prepare facilities for receiving aircraft. Whiteman Air Force Base in Missouri and Dyess Air Force Base in Texas will follow as additional operational bases. The Air Force plans to procure at least 100 Raiders, with some officials suggesting this number could increase if budgets allow and production proves efficient. This fleet size represents a massive increase in penetrating strike capacity compared to the 20 B-2s currently operational. Training programs for B-21 crews are already underway at Edwards, with personnel who will form the core of expertise that transfers to operational units when the bomber enters service. Initial operational crews will likely be drawn from experienced B-2 pilots who understand penetrating strike missions and stealth operations, though the B-21's advanced systems may have different training requirements. The combination of experienced personnel and cutting-edge technology should enable rapid development of operational capability once training infrastructure is fully established. For decades, Columbia was never seen as a major player in next-gen air combat. But that perception shattered when the nation quietly unveiled its involvement in Japan's revolutionary sixth-generation stealth project, unofficially dubbed the Godzilla jet. With cutting-edge features like microwave missile defense and AI-powered drone wingmen, this isn't just a fighter, it's a battlefield disruptor. How did Columbia get involved? What makes this jet so feared? Join us as we uncover how Columbia's Godzilla T-33 stealth fighter just shocked the world. At the start of the year, Columbia made headlines with one of its most ambitious defense moves in decades. The country announced a $3.9 billion agreement to acquire a fleet of Gripen fighter jets from Sweden's Saab. This decision will overhaul Columbia's air combat capabilities and redefine its role in regional security. Deliveries have begun, with 2 jets appearing at the prestigious Rio Negro Air Show in Antioquia in July. This marks a turning point for a military still operating decades-old Kfir aircraft. The Colombian Air Force is not just replacing planes, but stepping into a new generation of warfare. And the Gripen is no ordinary upgrade. The Saab Gripen is a multi-role combat aircraft designed for speed, agility, and adaptability. It's built around versatility, capable of switching between air-to-air, air-to-ground, and reconnaissance missions in a single sortie. This swing role functionality allows it to shift missions on the fly, responding to new threats with a cockpit optimized by its onboard computer systems. What makes the Gripen particularly effective is its aerodynamic design. It features a delta wing paired with forward canards, giving it high maneuverability and exceptional control even at low speeds or extreme angles of attack, up to 80 degrees. This design, paired with fly-by-wire digital controls, allows for tight turns, quick climbs, and evasive maneuvers that would challenge many fourth-generation aircraft. Speed and power are just the beginning. The Gripen is equipped with the PS-05/A radar system, which can track multiple targets simultaneously and guide a range of beyond visual range missiles. This radar, paired with the aircraft's electronic warfare suite, allows it to detect, jam, and evade threats while keeping the pilot fully informed in complex airspace. The jet supports a wide array of advanced weapons. It can carry the MBDA Meteor, a long-range air-to-air missile considered one of the most capable in the world. It's also compatible with the Iris-T short-range missile, AGM-65 Maverick for precision ground attacks, and the RBS-15 anti-ship missile. On board, a 27mm Mauser BK-27 cannon provides rapid-fire capabilities for close-range combat, although this is omitted in some trainer variants. The Gripen can carry more than 6,500 kilograms of weapons and gear, equipped with over 10 external hardpoints. Optional pods can be mounted for reconnaissance, targeting, or jamming operations, such as the Lightning Targeting Pod, Saab's modular reconnaissance system, or radar jamming tools like the Bright Cloud Active Decoy. The aircraft's survivability suite includes missile approach, warning sensors, and electronic countermeasures, giving pilots early alerts to counter incoming threats. Operationally, the Gripen was designed for speed in the air and on the ground. It can be refueled and rearmed by a small team in under 10 minutes, allowing for rapid turnaround between missions. It can take off from short or damaged runways, including remote airstrips, and is reinforced to handle rough landings. These features make it ideal for operations in challenging environments like Colombia's varied terrain. Its Volvo RM12 engine is a modular power plant derived from the proven GEF-404, offering high thrust and durability with low maintenance needs. The design has emphasized sustainability for decades, with Saab aiming for a 50-year service life supported by consistent updates and system flexibility. The Gripen's open architecture allows for easy software integration, meaning Colombia can upgrade the aircraft as new weapons and technologies emerge without needing to overhaul the platform. The aircraft is also fully compatible with NATO standard communication systems. It can link with satellites, drones, and allied units through encrypted channels such as Link 16 and Rover, allowing real-time data sharing across multiple platforms. This feature makes the Gripen a powerful multiplier in regional operations, joint exercises, or coalition missions. Colombian defense officials see the Gripen as a strategic response to growing regional tensions. As neighboring countries expand their fleets and invest in new technologies, maintaining air superiority has become more than a matter of pride. It's about deterrence. The Air Force has stated that Colombia cannot rely on outdated systems to defend its airspace, especially with the increasing role of drone warfare, electronic attacks, and long-range missiles in modern conflicts. However, the decision has not been without controversy. Many Colombians, particularly in political and civil sectors, have voiced concern about the timing and cost of the deal. With the country facing persistent issues in education, public health, and economic inequality, critics argue the government should focus on domestic welfare before allocating billions to defense. The Petro administration has defended the move, stating that the payments will be spread over multiple years to ease financial pressure. Officials have also pointed to the long-term benefits, including limited partnerships with Saab that could eventually strengthen Colombia's aerospace industry. While the jets will be manufactured entirely in Sweden, the agreement leaves room for future technology sharing and potential local integration of upgrades. Some critics have questioned why Colombia chose Sweden as a supplier, bypassing more traditional defense partners like the United States. But analysts say the decision may be strategic. By working with Saab, Colombia gains more flexibility and avoids dependency on one nation's military supply chain. Saab also offers export partners access to technical documentation and software code, allowing for greater control over long-term support and modifications. While headlines focus on the arrival of the Gripen, quiet conversations behind closed doors hint at something even bigger. Rumors suggest Colombia is already looking beyond its Swedish fleet, setting its sights on Japan's next-generation stealth fighter, the Godzilla FX fighter jet. The FX isn't just Japan's next fighter jet, it's a declaration of future air dominance, a twin-engine stealth aircraft designed with one objective: absolute superiority in the skies. According to Japan's Ministry of Defense, its performance pushes it beyond today's most advanced platforms, placing it firmly in the sixth-generation category. Larger than the American F-22, the FX isn't built for show. Its size allows for greater range, heavier payloads, and superior onboard systems. Much of its foundation comes from lessons learned during the X-2 demonstrator program, but the FX represents a leap forward in almost every direction. Every part of the aircraft begins life in a digital lab. Engineers simulate combat scenarios using 3D models and pilot feedback. Virtual dogfights expose weaknesses and shape improvements long before the prototype is built. Each change is stress-tested in high-fidelity simulations to ensure it performs under pressure. The FX integrates a network of sensors to detect stealth targets: AESA radar, infrared tracking, and passive RF detection. These systems are powered by gallium nitride semiconductors, boosting sensitivity and reliability. The FX not only detects threats at an extended range, but does so without giving away its position. Its defensive systems act instantly. Radar locks and incoming missiles trigger automated jamming protocols. Antennas embedded within the skin intercept threats and respond before human pilots even react. Stealth lies at the core of its design. There are no hydraulic systems, only electric actuators. These reduce weight, increase reliability, and help maintain the clean internal layout needed to avoid detection. The airframe features serpentine ducts and an internal weapons bay to eliminate radar reflections. Engine nozzles are coated with carbon-based material to absorb electromagnetic waves, further shrinking radar visibility. The jet also uses metamaterials, composites engineered at the microscopic level to bend and scatter radio waves. These materials work in tandem with a wave control system, rendering the FX nearly invisible until it decides to strike. The FX relies on passive detection systems and advanced sensor fusion to remain hidden. When radar must be used, it emits signals using low probability of intercept techniques. This electronic discipline allows it to operate freely in environments saturated with enemy sensors and missile threats. A breakthrough lies in the plasma stealth antenna system. It manipulates plasma fields to obscure radar reflections while still transmitting secure communications. This innovation gives the FX a decisive advantage, remaining undetected without going silent. Electric actuation replaces the complexity and vulnerability of traditional hydraulics. These systems are more flexible, resilient under combat conditions, and easier to maintain. They power key control surfaces and braking mechanisms, delivering precise response with reduced system weight. To streamline construction, the FX uses a fastenerless composite structure instead of mechanical fasteners, and adhesives bond carbon fiber materials into integrated components. This not only cuts weight, but also reduces production time and complexity. Heat-resistant alloys are placed strategically to protect against thermal stress near the engines. Simulation tools like finite element modeling allow engineers to optimize every component. According to Japan's Ministry of Defense, the mid-fuselage section alone saw an 11.6% weight reduction and a 66% cut in production labor. Rare feats in fighter development. Cooling is another major hurdle. High-powered electronics and dense avionics demand robust thermal control. A vapor compression cooling system combines air and liquid to prevent overheating, even during extreme performance or in hot climates. At the heart of the jet is the XF-9 engine, a new benchmark in military propulsion. Each unit produces over 33,000 pounds of thrust with afterburners and is designed to exceed 44,000 eventually. Despite this power, the XF-9 remains compact, 30% smaller in intake diameter than the F-2's GE F-110 engine. This allows all weapons to be carried internally, preserving stealth. Each XF-9 engine also generates 180 kilowatts of electrical power, 380 kilowatts in total. This surplus powers the FX's advanced systems and lays the groundwork for future technologies, including directed energy weapons and next-generation jammers. Agility is enhanced through 3D thrust vectoring nozzles, which deflect exhaust up to 20 degrees in any direction. This improves dogfight maneuverability and missile evasion. At the same time, the nozzle design suppresses infrared emissions, protecting the jet from heat-seeking weapons. In December 2021, Japan signed a landmark agreement with the United Kingdom to co-develop a demonstrator engine, combining IHI Corporation's experience with Rolls-Royce's profound expertise. Later, Italy's Avio Aero joined, turning the project into a tri-national endeavor. Together, the three nations aim to build an engine not just for flight, but for a new era of warfare. This engine will meet the extreme power and thermal demands of sixth-generation avionics, sensors, and future combat technologies. It will be compact, energy efficient, and durable, ready for the battlefield of tomorrow. Weapon integration is another frontier that the FX is already preparing for. Among its primary armaments will be the ASM-3, a high-speed air-launched missile developed for Japan's F-2 fighter, but now destined for the FX. The ASM-3 gives the jet long-range strike capabilities with high survivability, offering an ideal blend of speed and lethality as older platforms are gradually phased out. But beyond conventional missiles, the FX introduces a far more futuristic asset, a microwave-based directed energy weapon designed to neutralize incoming missile threats. This high-powered microwave system is not mounted as a separate cannon or pod. Instead, it's cleverly integrated into the jet's AESA radar system, activated through electron tube amplifiers that are both miniaturized and highly efficient. The result is a stealth fighter that can fry the electronics of incoming threats mid-air without compromising its stealth profile or maneuverability. As Japan lays the groundwork for the FX, it also prepares a whole ecosystem of support systems that will redefine how future air combat unfolds. At the center of this evolution is an ambitious unmanned systems program known as Combat Support Unmanned Aircraft, a project designed to bring loyal wingman drones into real-time coordination with manned fighters like the FX. These drones are built for flexibility. One variant focuses on sensing and reconnaissance and is equipped with sensors to detect, track, and designate targets from afar. The other version is weaponized, able to launch munitions or divert incoming fire, essentially acting as a shield for the FX. Despite having different operational roles, both drone types share the same basic airframe, reducing production complexity and allowing for interchangeable deployment strategies depending on mission requirements. This concept mirrors ongoing programs like the Kratos XQ-58 Valkyrie in the United States and Boeing's air-power teaming system. Still, Japan's approach emphasizes deep integration with the parent aircraft. The FX will act as the command hub, coordinating real-time tactics between manned and unmanned assets. This level of coordination will allow the FX to engage threats from multiple angles, saturate enemy defenses, or perform high-risk operations without endangering its pilot. Development of these support drones is underway, with full deployment expected by the 2030s, lining up with the FX's projected operational timeline. The fighter and its unmanned companions represent a shift toward networked warfare, where machines and pilots operate as one seamless unit. As Japan finalizes its design, tests propulsion systems, and scales up drone development, it is clear that the FX is more than a stealth fighter. It's the centerpiece of a next-generation aerial combat system, stealthy, intelligent, and supported by artificial intelligence-driven drones and electronic weapons. The origins of Japan's FX fighter program began not in a laboratory or factory, but in Washington. In 1997, the U.S. Congress passed the Obey Amendment, which blocked the export of the F-22 Raptor, then the world's most advanced fighter jet. Japan had sought the Raptor to modernize its air fleet. The request was denied. For Tokyo, that decision became a turning point. Cut off from acquiring the aircraft, which was believed to be essential, Japan made a choice. It would build its own. In 2009, the Ministry of Defense began a formal study on developing a next-generation fighter. The mission was bold. The new jet would not just match current fifth-generation aircraft, it would aim beyond them. It would be a sixth-generation stealth fighter, designed and led by Japan. The concept was called the I-3 fighter, for informed, intelligent, and instantaneous. It would connect with drones, ground systems, and airborne early warning aircraft. It would have radar strong enough to detect stealth targets. It would use gallium nitride semiconductors to increase radar power and clarity. Its controls would rely on flyby optics instead of traditional wires, processing vast amounts of information faster than ever. It would be fast, evasive, and aware. And it would be entirely Japanese. Japan needed to close a century's worth of technological gaps to build such an aircraft. The path forward began with the Mitsubishi X2 Shinshin, a demonstrator jet created to test and develop critical systems. The X2 first flew on April 22, 2016. After 2 years of test flights, Japan had gained the data it needed to take the next step. Japan invested in various focused research projects from 2009 onward. These were not experimental guesses. Each effort targeted a key system the fighter would need. Japan developed advanced sensors to detect stealth aircraft. It tested weapon bays that could open and release missiles at supersonic speeds without disrupting flight stability. Engineers worked on a lightweight but high-thrust engine, capable of powering not just flight, but onboard energy weapons and electronic systems. The XF-9 engine was born from this research, a compact but powerful core for the future fighter. In other labs, Japan explored how to defend against modern threats. It developed electronic warfare systems to jam or mislead missiles. It tested microwave weapons, designed to disable incoming threats before impact. It studied infrared imaging, thrust vectoring nozzles for extreme maneuverability, and airframe materials that could reduce weight without compromising strength. All this was more than theory. In 1929, Japan conducted test flights using F-2 aircraft fitted with experimental sensors meant for the FX. The results were promising. Japan was now preparing to move from concept to design, but the scope of the task ahead remained immense. Japan reached out to allies. In 2017, Tokyo and London signed an agreement to explore joint development. By 2018, Japan considered building its fighter alone, partnering with allies, or modifying an existing foreign design. Offers came in. Boeing proposed an upgraded F-15. BAE Systems offered a version of the Eurofighter Typhoon. Lockheed Martin proposed a hybrid of the F-22 and F-35. Northrop Grumman expressed interest, sparking speculation that it might revive its long-abandoned YF-23 Black Widow design. Japan listened, but was not convinced. The Ministry of Defense rejected all three proposals. Existing fighters could not meet Japan's demands for stealth, speed, and future growth. Lockheed's F-22/35 hybrid was powerful, but too expensive. The U.S. was still unwilling to loosen export restrictions. By early 2019, Japan declared it would lead the program itself. The FX would be Japanese and built at home, but international partners would still be welcome on Japan's terms. Mitsubishi Heavy Industries was placed at the helm. The Acquisition, Technology and Logistics Agency formed a dedicated FX team, led by a JASDF Major General and staffed with elite engineers and officers. Subaru Corporation established a new tech center to support the effort. The first prototype would be built by 2024, and flight testing would begin in 2028. Full production would follow by 2031. Japan had allocated over 28 billion yen to launch the program by 2020. A new fighter image was released, and the project officially became FX. Its design would allow rapid upgrades, modular components, and compatibility with future unmanned systems. It would be the heart of Japan's air defense into the mid-21st century. Then in late 2022, the FX's future took a new turn. Japan, the United Kingdom, and Italy announced a merger of their fighter projects. The FX, the UK's Tempest, and Italy's sixth-generation concepts would combine into a single multinational program, the Global Combat Air Program. This historic decision marked the end of the FX as a standalone national project, but it was not a retreat. It was an evolution. Japan would bring its technologies, sensors, engines, and microwave weapons to the global table. Together with Rolls-Royce and Leonardo, Japan would now help shape the future of air combat on a much larger stage. From denied access to U.S. technology to forming one of the decade's most advanced international defense programs, Japan's fighter story is no longer about catching up. It's about leading. Production of the prototype was expected to begin in 2024. Flight testing will follow in 2028. Mass production is planned for 2021. The United States' new sixth-generation bomber, the B-21 Raider, has captured global attention for its advanced technology and lethal capabilities. Now rumors suggest that North Korea may have acquired one, acknowledging its sophistication, which has sparked worldwide curiosity. On the other hand, China, a longtime rival of the US, has expressed concerns over the Raider's strategic potential, further fueling global debate. Does North Korea truly possess the B-21 Raider in its arsenal? Can China's upcoming H-20 bomber rival the Raider in stealth, range, and technology? Join us as we explore the capabilities of the United States B-21 Raider that the whole world is afraid of. Although it's unlikely for North Korea to ever acquire the B-21 Raider, the nation has expressed both respect and concern for this advanced bomber. A recent report from North Korean state-run media has revealed the growing concerns about the United States military's new stealth bomber, the B-21 Raider, which made its first test flight in November 2023. According to the Rodong Sinmun newspaper, this new bomber is being seen as a very serious nuclear threat, strikes showing the world that Washington is willing to use its nuclear weapons in unexpected ways. North Korea's state media emphasized that the B-21 has the ability to launch an unexpected nuclear strike anywhere, a phrase that suggests its advanced capabilities in stealth technology and nuclear strike precision. Also, the test flight of this new generation of strategic bombers is a clear demonstration of the United States putting its nuclear preemptive strike tactics into practice. Such a development sends a powerful message, and anyone can easily guess the implications of the U.S. showcasing this new weapon. The journey to create the B-21 Raider began in 2011, setting the stage for a fierce competition between two aerospace giants, a Boeing-Lockheed Martin partnership and Northrop Grumman. Both companies presented their visions for the next-generation stealth bomber, but Northrop Grumman's extensive experience with the B-2 Spirit and its promise of affordability gave it the winning edge. The Air Force ultimately awarded the contract to Northrop Grumman in 2015, impressed by the company's ability to balance advanced capabilities with economical costs, a lesson learned from the astronomical expenses of the B-2 program, which saw each aircraft priced at amounts comparable to the GDP of some small nations. To meet the Air Force's demanding requirements while keeping costs in check, Northrop Grumman assembled a vast network of over 400 suppliers from 40 states. This collaboration spanned years, including the challenging period of the COVID-19 pandemic, with suppliers operating continuously to ensure progress. Among these suppliers were 7 globally renowned Tier 1 companies. These included Pratt & Whitney, known for its advanced jet engines, Europe's largest defense contractor, BAE Systems, Spirit Aerosystems, the leading manufacturer of aerostructures, and other major contributors like Northrop Grumman's Orbital ATK, Rockwell Collins, GKN Aerospace, and Janicki Industries. Together, these companies and Northrop Grumman developed a stealth bomber, the B-21 Raider. With a unit cost of $630 million, this bomber is not only 68% more cost-effective than the B-2, but also significantly more advanced. This achievement reflects over 2 decades of technological progress, making the B-21 a marvel of modern engineering. Despite its affordability compared to its predecessor, the B-21 retains unparalleled capabilities that redefine what a stealth bomber can accomplish. What makes the B-21 Raider especially significant is its long development period. The aircraft has been in the works for over 30 years, and its name is a tribute to the Doolittle Raid, a famous World War II mission which was led by Lieutenant Colonel James Doolittle. In 1942, Doolittle led a bombing raid on Japan, which marked a critical moment in the war. By naming the new bomber after this historical event, the U.S. sends a symbolic message about its commitment to strategic military power and its readiness to act when necessary. The U.S. Department of Defense has repeatedly stated that the role of its nuclear weapons is to deter nuclear attacks on the nation and its allies. According to the Pentagon's 2022 Nuclear Posture Review, the U.S. would only use nuclear weapons in extreme cases to defend its vital interests or those of its partners. However, the development of the B-21 Raider and other advanced military technologies shows that the U.S. is preparing for scenarios where it may need to carry out preemptive strikes to protect its security. On the other hand, North Korea has remained defiant in its nuclear stance. In September 2022, the country codified its irreversible nuclear weapons program into law, which includes provisions for the preemptive use of nuclear weapons. North Korea's leadership has repeatedly stated that it may resort to nuclear strikes if its leadership or nuclear infrastructure is threatened by hostile forces. This law further escalates tensions in the region, with North Korea maintaining its aggressive stance in nuclear weapons development. The military presence of the United States in the region has increased in recent months as part of efforts to deter North Korean aggression. American bombers such as the B-22 Stratofortress have made notable appearances over the Korean peninsula, including a landmark landing in South Korea on October 17, 2023, the first time in 30 years. This was followed by a joint aerial exercise involving the B-52, U.S. F-16 fighter jets, and South Korean F-15K Slam Eagles. These maneuvers were intended to strengthen military cooperation between the U.S., South Korea, and Japan in response to North Korea's missile and nuclear provocations. Washington, Seoul, and Tokyo have repeatedly emphasized their commitment to working together to prevent North Korea from continuing its nuclear and ballistic missile tests. North Korea's missile activity has been relentless, with 23 ballistic missiles fired in just 15 days in 2023 alone. These ongoing tests are seen as a direct challenge to regional stability, and the U.S. and its allies are determined to prevent further escalation. Earlier this year, North Korea claims it has tested a new intermediate-range ballistic missile equipped with a hypersonic warhead, saying it can contain any rivals in the Pacific region. The missile, launched on Monday, was the first test in 2 months and coincided with U.S. Secretary of State Antony Blinken's visit to Seoul for discussions with South Korean leaders. Hypersonic weapons, capable of traveling over 5 times the speed of sound, are hard to detect and intercept. North Korea says this missile reached speeds 12 times faster than sound and flew 1,500 kilometers. However, South Korea's military reported it traveled 1,100 kilometers before falling into the sea and condemned the launch as a provocation. Pyongyang claims the missile has advanced features like a new flight control system and a carbon fiber engine. Leader Kim Jong-un stated the launch demonstrated North Korea's readiness to protect its interests. Why is North Korea worried about the United States' next-generation bomb? Let's move on to features of this next-generation bomber. In terms of design, the B-21 Raider shares some similarities with its predecessor, the B-2 Spirit. Both aircraft feature a bat-like tailless shape, a design that minimizes radar detection by avoiding sharp angles. However, there are important differences. For instance, while the B-2 has its engines placed further away from the body of the aircraft, the B-21's engines are located closer to the wing root, where the wing and fuselage meet. This shift in engine placement is a key design decision, allowing for better stealth and efficiency. The engine air intakes of the B-21 are also distinct, angled differently compared to the B-2's serrated intakes. Additionally, the B-21 is designed with overwing exhaust to mask the infrared signature of its engines, a feature not seen on the B-2. Interestingly, this overwing exhaust design was first proposed in an artist's rendering of the B-2 back in 1988, showcasing how ideas have evolved over time. The B-21's size is expected to be similar to that of the B-2, which makes it likely to be a 4-engine bomber. This size would give it a large payload capacity, necessary for carrying both conventional and nuclear weapons. In 2016, Pratt & Whitney was announced as a subcontractor for the B-21, confirming that it would use one of 2 engine types, the F-100 or the F-135. The F-100, which powers the F-15 Eagle fighter jet, is a proven, reliable engine. However, the Air Force might opt for the F-135, the same engine used in the F-35 Joint Strike Fighter, due to its growth potential and the opportunity to streamline maintenance costs across multiple aircraft platforms. Like its predecessor, the B-21 will be a strategic bomber capable of carrying both nuclear and conventional weapons. Given its similar size to the B-2, the B-21 will likely feature 2 bomb bays. To keep costs under control, the Air Force may reuse the Advanced Applications Rotary Launcher from the B-2, which fits in each bomb bay and can carry up to 8 bombs or missiles. This will ensure that the B-21 can carry a substantial payload, making it an effective asset for long-range bombing missions. One of the most important features of the B-21 will be its role in nuclear deterrence. For this mission, the Air Force will likely equip the B-21 with the Long-Range Standoff Missile, a precision-guided nuclear weapon designed for long-range strikes. This missile will allow the B-21 to strike high-value targets with minimal risk, as it will be launched from a distance, beyond the reach of enemy defenses. The second weapon is the B-21 series of nuclear gravity bombs, particularly the new B-61-12, which has a unique dial-a-yield capability. This means that the power of the bomb can be adjusted to fit the target, allowing for precise and flexible attacks. In a typical nuclear mission, the B-21 will use its stealthy LRSO missiles to clear a path through the enemy's air defenses before dropping B-61 bombs on primary and secondary targets, ensuring maximum damage while minimizing the risk to the bomber. In addition to its nuclear capabilities, the B-21 will also be able to carry out conventional missions, making it a versatile weapon system. For these operations, it will be armed with the Joint Air-to-Surface Standoff Missile Extended Range, a long-range conventional cruise missile, as well as the 2,000-pound GBU-31 Joint Direct Attack Munition bombs, which are guided by satellites to strike targets with pinpoint accuracy. The B-21 will use these weapons in a similar way to its nuclear weapons, first blasting its way through enemy defenses with the JASSIS MERs, and then delivering JDAMs to destroy critical targets. In some missions, the B-21 could serve as a missile truck, launching up to 16 JASSIS MERs from a safe distance. Alternatively, it could fly into less defended airspace, using its stealth to penetrate enemy lines and deliver JDAMs directly onto the target. Additionally, the B-21 will carry the Massive Ordnance Penetrator, a 30,000-pound bomb that is currently only carried by the B-2 bomber. This massive bomb is designed to penetrate deeply buried or hardened targets, and the B-21 will be able to carry and deploy it, expanding its ability to take on a wide range of tough missions. One of the most innovative features of the B-21 Raider is its open architecture design. Unlike previous bombers, the B-21 is being built with a flexible hardware and software system that can easily be updated over time. This means that the bomber will not be limited to just one role, but can evolve as new technologies and missions emerge. The B-21's weapons bay could eventually transform into a mission payload bay, capable of carrying not only bombs and missiles, but also surveillance equipment, communication systems, drones, and electronic warfare packages. This makes the B-21 adaptable to many different roles, particularly in denied or contested environments where traditional bombers might struggle. As a result, the B-21 Raider is on track to become the first multi-role bomber for the United States, capable of executing a variety of missions far beyond its initial nuclear and conventional strike capabilities. The B-21 is expected to take to the skies in the mid-2020s, with the Air Force planning to acquire at least 100 of these bombers to replace older models like the B-52-0H Stratofortress and B-1B Lancer. A larger fleet of up to 200 bombers is possible, depending on funding and budget considerations. However, the exact details of the B-21's design and capabilities remain highly classified, as the U.S. military wants to protect its technological advantages. The B-21 has effectively disappeared into the black world of military technology, with the public only expected to see it once it is fully ready for service. When it does reemerge, however, it will mark a major leap forward in both the bomber's operational capabilities and the future of air combat. Now, let's compare the capabilities of this U.S. bomber with those of China's next-generation bomber. The competition between the United States and China in the development of next-generation bombers is intensifying, with both nations striving to establish dominance in stealth technology, firepower, and aviation innovation. At the heart of this race are the American B-21 Raider and China's Xi'an H-20 bomber, two of the most advanced strategic bombers ever conceived. The Chinese H-20 has been in development for several years, with its initial renderings emerging around the same time as those of the B-21 Raider. Analysts believe that China's future position in strategic bombing depends heavily on the success of the H-20. The aircraft is expected to be a key component of China's military modernization, aiming to rival or surpass the capabilities of its American counterpart. However, the United States, with its decades of experience in designing stealth aircraft, has a considerable head start. The B-21 Raider, on one hand, incorporates advanced design features such as serrated skin panels, fiber matte coatings, and a flying wing shape to minimize radar detection. Its engines are cleverly concealed to reduce infrared visibility, and it will be painted with anti-reflective materials to blend seamlessly into the sky during daylight operations. At altitudes exceeding 50,000 feet, Its dark underside ensures that it merges with the upper atmosphere. An onboard light sensor further enhances its stealth capabilities, allowing pilots to adjust altitude in response to changing light conditions. To maintain these advanced stealth features, the B-21 may require specialized storage in air-conditioned hangars, costing millions of dollars. China's H-20, on the other hand, is expected to employ a flying wing design similar to the B-21, leveraging lessons from the J-20 stealth fighter. It will likely incorporate advanced radar cross-section reduction features, including a chimed forebody, a modified radar radome, and an electroconductive canopy. Other features such as serpentine air ducts, a flat fuselage, and sawtooth edges are expected to contribute to its stealth performance. However, the United States has a significant advantage in stealth technology, with the F-35 and B-2 Spirit already setting benchmarks in radar evasion. The B-21 Raider is designed to be even stealthier than these predecessors, making it a formidable challenge for China to match. The B-21 is expected to feature state-of-the-art avionics, providing unparalleled situational awareness, communication capabilities, and integration with other military assets. Its sensors and data sharing systems will make it a central component of a networked battlefield, enhancing its role beyond that of a traditional bomber. But some of its key features include a multi-mode radar, a fully digital navigation system that combines a terrain-following radar, GPS guidance, and an astro-inertial navigation system. This last feature allows the B-21 to navigate using celestial bodies in space, ensuring precise operations even in challenging environments. The bomber is also equipped with an active electronically scanned array radar, an electronic warfare system, a distributed aperture system, and an electro-optical targeting system. These advanced sensors and systems provide unmatched situational awareness, enabling the B-21 to detect, track, and engage targets effectively. To support battlefield communication, the aircraft uses Link 16 and a high-frequency satellite link, ensuring real-time data sharing with other assets during missions. One of the B-21's most remarkable innovations is its defensive management system. This system alerts the flight crew to potential threats in the area, allowing them to make mid-flight adjustments to their mission plan. The aircraft can quickly process new information, rerouting its course to minimize exposure to detected dangers. This capability ensures the safety of the crew and increases the bomber's survivability in high-threat environments. The B-21 is also designed to act as a key player in the sensor fusion network, making it not only a powerful bomber, but also an effective battle manager. This integration enables it to gather, process, and share data with other assets in the fleet, enhancing overall mission effectiveness. For maintenance and reliability, the aircraft features an onboard test system that continuously monitors the performance of thousands of components, ensuring optimal functionality throughout the mission. In terms of firepower and operational range, the B-21 Raider is designed to carry a diverse array of nuclear and conventional weapons. Its long-range capabilities enable it to strike targets anywhere in the world without requiring in-flight refueling, making it a versatile and strategic asset. The H-20, on the other hand, is expected to focus on regional power projection, with an emphasis on targeting U.S. military installations in the Pacific. While it may have strong operational range and payload capacity, it is unlikely to match the global reach and versatility of the B-21. In terms of armament, the B-21 is built to carry over 30,000 pounds of weapons, making it a formidable force on the battlefield. Its arsenal includes advanced nuclear weapons like the B-61 variable yield gravity bomb and long-range standoff nuclear cruise missiles. Additionally, it can carry a variety of conventional weapons, including Lockheed Martin's long-range anti-ship missile and Boeing's GPS-guided joint direct attack munition. These weapons allow the B-21 to engage targets from long distances, making it a versatile and stealthy platform capable of operating in contested areas like the South China Sea. In comparison, China's H-20 bomber, while still shrouded in secrecy, is believed to have similar capabilities, though its specifics remain unconfirmed. Reports suggest it may carry up to 20,000 pounds of armament, enabling it to threaten U.S. targets as far away as Hawaii. However, the B-21 currently has an edge in terms of confirmed capabilities and technological advancements, giving the U.S. a significant strategic advantage. The Kremlin has finally decided to go head-to-head with the top nations like the United States and China in producing a new stealth bomber that is about to change the game. The concept of war has historically favored the team that dominates the skies, and Russia seems well poised to strike fear into the hearts of potential opponents with its new bomber. How did the world react to the sight of the behemoth? Could Russia be on the verge of triggering another arms race? Join us as we discuss the amazing features of Russia's new stealth bomber. Rumors of Russia's new stealth bomber have taken a stranglehold of worldwide military space since the early 2020s. However, the wait is finally over. It is coming, and it is a monster. Unlike the very first types of Russian bombers, including the Tupolev Tu-95 and the Tupolev Tu-160, which rely on brute lethal force and speed as their greatest features, the new Russian stealth bomber, PAKDA, relies on invisibility as its greatest feature. Just how does anyone fight a bomber they cannot even see? Although rumors of this bomber became prominent in the 2020s, the Kremlin has secretly had it in the works since the late 1990s, when the Russian government decided on a need for a new strategic bomber with different types of technical and tactical requirements compared to its predecessors. Having drawn out a design for the bomber, the Russian Air Force needed to come to a decision about which company should be given the privilege of building the Kremlin's next-generation bomber. After many deliberations, they came to a unanimous decision to have the bomber built by Tupolev Design Bureau in 2007 before the finances were released to fund the project in 2008. However, questions begin to linger about the details of the design, especially after rumors of a possible replication of the Tupolev Tu-160, owing to its ability to travel at supersonic speed. But it was soon debunked by a public address from then Prime Minister Vladimir Putin, who implied that the new bomber would be a completely different design, which was an exciting prospect as well, since the United States and China had just unveiled their B-21 Raider and the H-20 respectively. Although there has been no press release or any form of publication confirming that the new stealth bomber was a direct geopolitical message to the forces of the West, which have consistently flexed their military might, there are theories stemming from Russia that the new bomber was an example of Russia taking the lead in the arms marathon that has silently been afoot since the World War. From Vladimir Putin's interview, it was almost too easy to tell that this was more than just some aircraft. It was a geopolitical weapon with a direct message of mutually assured destruction to the West. While the Raiders and the H-20s have dominated aerial warfare for a long time, owing to their beastly presence in combat, how much of a threat is Russia's new PAKDA bomber? Like General Giulio Douhet once said, "He who controls the air controls everything," and Russia is definitely not oblivious to the fact. Ergo, the deliberation to create a bomber that matches up to the intensity of Raiders and H-20s. The Russian Air Force had quickly figured out that aerial warfare was moving slightly away from speed and creeping towards more intelligence, surveillance, and reconnaissance, or ISR warfare. Hence, they followed suit with the proposal of creating their own stealth bomber, capable of producing both hunter and killer functions. For some context, the Tu-160, manufactured by the same company in charge of the new stealth bomber, was designed to be a hunter mission bomber aircraft. It is a supersonic, variable sweep-wing, nuclear-capable heavy strategic bomber designed for hunter missions. It was commissioned to service in 1987, serving as both a conventional and nuclear bomber, following the requirement of the Soviet Union in 1967. The Tu-160 was designed with the perfect aerodynamic cheat code with the deliberate attachment of a variable geometry wing. The variable geometry wing, or swing wing in popular parlance, was designed to optimize all levels of movement, ranging from takeoff and landing to cruising. For instance, when the wings are in full extension, they give low-speed stability and do not require the regular length of a runway to take off or land. Hence, it makes it easier for the Tu-160 bomber to operate from varied airfields and carry huge payloads. While there is a huge chance that the bomber's aerodynamic wings could be optimized or manipulated to perform hunter missions, its sheer size negates its potential impact on avoiding the A2AD aircraft defense mechanism used by most top nations. Although the swing wings are relevant to attaining low-speed stability, When they are swept back, the aircraft becomes more aerodynamic and can attain and sustain supersonic speed, with little to no drags, as the aircraft travels at Mach 5. The Tu-160's ability to perform a wide range of missions because of its flexibility has made it a threat to the West and the big players in the Indo-Pacific regions, like China. Its mission flexibility gives it wiggle room to go from subsonic speed to supersonic, making it the best of both worlds, and op countries around the world have struggled to keep up with it. However, that just wasn't enough for the Kremlin. They wanted more, or maybe less, considering the fact that they want the PIKDA to focus on stealth more than speed, and reaching that decision by enforcing the decision that it is only retrofitted with subsonic speed. On September 3, 2009, the Russian Defense Ministry awarded Tupolev Design Bureau a 3-year research and development contract to undertake studies for the new long-range bomber. According to the President General Designer of Tupolev, Igor Shevchuk, this should be a fundamentally new aircraft based on conceptually new solutions. However, for a country with the number of aircraft and bombers that the Kremlin possesses, there is always going to be that one voice who questions the need for more. For some context, on June 12, 2012, then Deputy Prime Minister Dmitry Rogozin questioned the need for a new long-range bomber, pointing out the immense progress that Russia and their archenemy, the West, were making in aerial and anti-missile defense technology, reinforcing his point that spending billions of taxpayers' money on an aircraft when they know the difficulty of breaching these new aerial defenses. Although he had made his point, the Chief of the General Staff, Nikolai Makarov, responded by stating that the Kremlin's intention to put in the work and build this bomber revolves around creating a monster behemoth in the air that is much more superior to the United States. His statement was indirectly backed up by President Vladimir Putin on the 14th of the same month, who hammered on the importance of getting a new long-range bomber regardless of the impact of the Tupolev Tu-160s. By 2013, the PAKDA team had finally reached a decision to focus on the stealth options on the PAKDA, while also giving it a subsonic flying wing. Although there were published articles going against the decision to only add a subsonic flying wing, the rationale behind it was pretty simple. Russia already has bombers capable of subsonic and supersonic speed. Hence, they wanted something different in speed and size, but just flexible enough to perform both hunter and killer missions in a single run. The PAKDA's flying wing is a tailless, fixed-wing aircraft that has no definite fuselage, with its crew, payload, fuel, and equipment housed inside the main wing structure. However, it would have various small protuberances such as pods, nacelles, blisters, booms, or vertical stabilizers. The design gives the aircraft a flat shape while flying at the speed of a regular commercial plane, making it nigh impossible to detect by radar. However, the aircraft is much more potent than the deliberately shunted speed limit on the subsonic level. For a hunter mission, its ability to travel at the same speed as an airplane while having a flat shape, looking almost like a single wing hovering in the skies, gives it the advantage and leverage to get closer to its mark when it needs to perform killer missions. This design struck the perfect balance between stealth missions and killer missions. Although the designs bordered along the lines of perfection, there was one hiccup. How exactly does the flat-back plane hide all of its payload without drag and also be able to deploy hypersonic missiles without getting spotted? The Russian Defense Ministry had designed the flat-back bomber with stealth and killer missions in mind. Ergo, they found ways to integrate the fuselage and other parts of the aircraft into the flying wing, drawing inspiration from the single-bay design of the American B-2 Spurt, their direct competitor. But how does a subsonic flying wing aircraft carry and unleash a payload of hypersonic weapons and hit its target? The rationale was rather simple. Since the missions were flexible, meaning that the aircraft could be on a double mission in one run, hunting and killing its targets, the payloads are tucked neatly in the aircraft's body, making it impossible to spot even with A2AD aerial defenses. While the plane flies at subsonic speed and gets closer to its mark, the bay opens and the hypersonic missile is dropped on its target. However, the missile isn't fired from the aircraft. Instead, it is released at normal speed. Then the engine on the missile sets it up to go faster than Mach 5 and explodes on impact. The aircraft was designed to carry payloads the size of the Kh-47M2. The Kh-47M2 is a Russian air-launched ballistic missile with an estimated range of 460 to 480 kilometers and a reported top speed of Mach 10, which is twice the speed of sound. It can carry either conventional or nuclear warhead and can be launched by two 22M3 bombers, MiG-31K interceptors, modified Su-34 fighter bomber, and very soon the PAK-DA. Even before the advent of the PAK-DA, the Kh-47M2 had already been deployed on numerous war missions by the Russian Air Force. However, its most recent deployment has taken the most sting out of the West in the ongoing war between Russia and Ukraine. The United States has openly supported Ukraine and given them war support to keep them in a fight with Russia, who apparently has the stronger military and better military weapons on land, air, and the seas. However, during the Biden-Harris administration, President Joe Biden, in March 2022, confirmed that Russia deployed hypersonic missiles in Ukraine, which he described as almost impossible to stop. The message was clear. Russia has a missile that is nigh untrackable, making them even more dangerous than they were. And this time, they are in the process of manufacturing a flying-wing subsonic bomber that easily escapes the radar and is capable of carrying the Kh-47M2. This perfectly balanced bomber was more than just technology. It was a message well received from Russia to the rest of the world. However, it wasn't until April 2014 that the head of Russia's United Aircraft Corporation, otherwise called UAC, Mikhail Pogosyan, announced that the Tupolev Design Bureau had finalized the design and that the project was moving to the intermediate phase, signaling the completion of the design and construction of a prototype. And that was Russia's first hiccup. The Russian Defense Ministry demanded 5 billion Russian rubles to prepare the Kazan Aircraft Production Association plant in Kazan. As expected, the old voices of reason, who believed that the country already had enough long-range bombers, were back asking the same questions. However, the Kremlin responded by releasing the requested 5 billion Russian rubles, which were allocated to reconstructing and re-equipping the Kazan Aircraft Production Association plant in Kazan. While it was widely reported in Russia that the first full-size model of the bomber was built, amongst various scale mock-ups of different configurations on March 1, 2017, it wasn't released openly, hence the public only had verbal knowledge of the aircraft. It wasn't long before doubt had started to set in, with rumors of PAK-DA being a ruse making the rounds. However, in July 2018, the United Engine Corporation, otherwise called the UEC, and Tupolev, the company that was commissioned with the responsibility of building the PAK-DA, revealed that they had just signed a contract for the creation of the bomber's power plant. However, questions lingered on how they decided to create the power plant. Was it going to be some new groundbreaking idea, or was it going to come from an already established engine? Soon there were released reports that suggest a possible upgrade from the Kuznetsov NK-32 engine. In the same year, the Kremlin reportedly allocated 8 billion Russian rubles for the development of this new engine, which was contracted to JSC Kuznetsov in Samara. Although the specifications of the engine have been a well-guarded secret, its potential performances have been heavily publicized. The engine is rumored to provide the PAK-DA with the required force to perform a 30-hour non-stop mission without having to refuel. But it gets even better, as it also comes with a temperature-resistant feature, protecting it from the effects of a nuclear explosion and a service life between 12 to 21 years. While the engines remained in construction, the PAK-DA's final draft was finally approved, and the construction in the plant began in late 2019. Although Tupolev kept the construction process away from the media, Russia's state-owned news agency, the TASS, reported on May 26, 2020, that the very first PAK-DA, which will be the finished article, was already in construction and will be finished in early 2023. Although Tupolev were the leading constructors, they had help from companies like NPP's Vesta, which announced at the 2021 Max Air Show that his company was in the process of completing the construction of the PAK-DA's ejection seats and hoped to hand them over to Tupolev in 2023, the proposed date for the first sighting of the massive aircraft. While speculations of the KH-47M2 being the main hypersonic weapon to be fitted into the PAC-DA's weapons bay had consistently made the rounds on the internet, on August 2021, it was announced that a new long-range, nuclear-capable hypersonic cruise missile, the KH-95, was under development to be fitted inside the PAC-DA's weapon bay. Although the Kremlin has earmarked aerial warfare dominance, specifically over the United States, as the reason for funding the creation of the PAK-DA, there is growing evidence that the possible integration of a hypersonic missile carrying a nuclear warhead might be an overkill, but is capable of changing aerial warfare forever. Could Russia finally take the giant leap over the United States and China, who have recently been at the top of the food chain in aerial combat? Could the creation of the PAK-DA spark a new global arms race? While the world holds its breath in grievous anticipation of Russia's release of the PAK-DA, the United States and China have decided to raise the stakes even further, especially the United States, who are now looking to upgrade their long-range bombers. But just how does their Northrop Grumman B-21 Raider fare, in contrast with the PAK-DA? America developed its Long-Range Strike Bomber, or LSB program in 2011, with only one goal in mind: aerial dominance. Over the years, aerial warfare has hit a fever pitch, and there is no bringing it down. Hence the hot pursuit of top countries who are looking to not only get in on the action, but be at the very top of the food chain. Hence America's decision to come up with the B-21 Raider. The Raider is proposed to be a stealth intercontinental strategic bomber that can deliver conventional and thermonuclear weapons. Named Raider in honor of the Doolittle Raiders of the Second World War, the B-21 is meant to replace the Rockwell B-1 Lancer and Northrop B-2 Spirit by 2040, and possibly the Boeing B-52 Stratofortress after that. Although, just like the PAK-DA, the B-21 Raider has been touted for a release in 2023, especially since the first flight of the Raider already occurred on November 10, 2023, and 3 of them, which were considered airworthy, were involved in program testing in September 2024. However, neither nation has fully released their new bombers. Although there are reports of technical delays, like with the PAK-DA, where the sanctions following the Kremlin's invasion of Ukraine, starting the Russo-Ukrainian War in 2022, have been rumored to halt their momentum, and the B-21 Raider has been touted to be undergoing early-stage flight testing, there are other geopolitical rumors that have effortlessly made the rounds in the media. For some context, there are speculations that both countries are in the middle of a game of chicken, seeing who blinks first, with hopes that the first release is assessed by the other country, who then upgrades theirs to remain on top of the food chain. Although the speculations seem to have stuck because neither nation has presented their aircraft in the timeline that they proposed, Russia has come flying out of the gates in a rush to defend their position. Russian Deputy Prime Minister Denis Manturov has openly discussed the common struggles with schedules around the world, but he assures Russia and the entire world that the sanctions following the 2022 Russian invasion of Ukraine would not affect the timing of the creation of the PAK-DA, as the bomber does not contain any foreign components. Although he made these bold claims in 2022, promising that the aircraft would be completed by 2026, with a prototype ready by 2023, as of June 2025, there are still no reports of a prototype. While the world waits for this new stealth subsonic behemoth bomber capable of hosting and launching hypersonic missiles with nuclear warheads, the potential reaction of other top countries remains to be seen, as aerial warfare might change forever. There is a lot at stake for Russia, and that's the idea. The United States has now rolled out a new generation of stealth bomber that doesn't just test limits, it changes them. This stealth bomber is made to go undetected, strike from incredibly long distances, and survive within the most contested airspace on the planet, even in today's modern warfare. What does this mean for the world as military technologies evolve? Is the United States taking a defensive or an offensive technological leap forward in global affairs? Join us as we explore the hidden powerhouse that's designed to strike without warning. Ever since the Cold War wrapped up, America has looked at its big bombers as more than just flying weapons. These aircraft serve as massive calling cards that communicate global reach and serious intent. The trusty old B-52 has been around forever. The sleek B-1B could really move. And then there's the B-2 Spirit. This almost alien-looking aircraft cost more than some countries' entire defense budgets. For decades, these planes owned the skies. They could haul nuclear weapons anywhere on the planet, and most enemies knew better than to mess with them. But time doesn't stand still, especially in warfare. Those aircraft began to show their age. And meanwhile, other countries weren't just sitting around. They were building air defense systems that could pose a real threat to America's flying fortresses. It became evident that the United States needed something completely fresh. Not just another upgrade or patch job, but a bomber built from scratch to handle whatever the next few decades might throw at it. After more than 30 years without designing a new strategic bomber, America finally had its answer, the B-21 Raider. And they have been working on this thing in almost total secrecy. The kind of project that makes people wonder what else is being developed behind closed doors. The B-21 is not just another bomber, it is a game changer in military aviation. It is built for long-range missions, designed to stay undetected, and capable of striking targets with incredible precision. In today's world, where speed and stealth matter more than ever, this aircraft is made to operate where others can't. However, reaching this point was not easy. The technology, design, and strategy behind it are the result of years of testing and innovation, shaping the way the United States approaches air combat. Back in the 1970s, the United States set out to develop a new bomber that could eventually replace the B-52, which had already secured its place in history. The result was the Rockwell B-1, a supersonic bomber built for speed and low-altitude missions, designed to evade enemy radar. At the time, it was a significant advancement, but technology continued to evolve. Radar systems became more precise, missiles got deadlier, and the challenges for stealth bombers continued to grow. As threats changed and global tensions shifted, so did American priorities. Every new bomber was more than just a reaction to emerging enemies. It was a message. By 1977, people started losing faith in the whole idea of strategic bombers. President Carter's team looked around and saw these increasingly sophisticated air defense systems popping up everywhere. Cruise missiles were also becoming a bigger deal, and bombers seemed like they were heading toward irrelevance. The B-1 program, which had been this shining example of next-generation speed and raw power, got shut down completely. Then Reagan walked into the White House, and everything flipped. Cold War tensions cranked back up to 11, and suddenly the arms race was in full swing again. The B-1 program came roaring back to life, but this time as the B-1B Lancer. Sure, they had to dial back the top speed to Mach 1.25, but that compromise bought them something valuable. The aircraft received significantly improved protection against air defenses, and they could be built quickly. Within 6 years, they'd rolled out more than 100 units. It was classic Reagan-era thinking. While the B-1B was entering service, another project was taking shape behind closed doors. Northrop Grumman engineers, working under extreme secrecy, were building something even more advanced, an aircraft that would not just avoid detection, but would practically disappear from radar. The result was the B-2 Spirit, a breakthrough in stealth technology. Its flying wing design, lack of a vertical tail, radar-absorbing coatings, and heat-dampening structure made it one of the most complex aircraft in the world to track, let alone intercept. It was nearly invisible, living up to the name Spirit in every way. That level of stealth came at an enormous cost. Each B-2 was initially priced at about $2,130 million, and today, when adjusted for inflation, that figure jumps to over $4,300 million. Lawmakers were shocked, and with growing pressure to control defense spending, Congress cut the original plan to build 132 bombers down to just 21. Even the hangars had to be re-engineered with tightly controlled climate systems just to preserve the aircraft's stealth coating. Every aspect of the B-2's development was a financial and logistical challenge, one that sparked both admiration and debate. Despite its massive cost, the B-2 showed exactly why it was worth every dollar. It could fly deep into enemy territory without being detected, making it a key player in precision strikes and critical missions. But it wasn't just another bomber, it was a statement of American technological superiority. In modern warfare, visibility can mean vulnerability. And the B-2 proved one thing: the most dangerous threat is the one that goes unnoticed. During the North Atlantic Treaty Organization bombing campaign against Yugoslavia in 1999, just 3 B-2 Spirit bombers took off from Missouri. They carried out about 11% of all coalition airstrikes. These long-range missions were executed with pinpoint accuracy and 0 losses, leaving both allies and adversaries in awe. Later, the B-2 proved its capabilities again in Iraq, Afghanistan, and Libya, launching strikes directly from United States soil and returning home, all without relying on foreign air bases. It was a force to be reckoned with, fast, precise, and nearly unstoppable. Over time, even the Spirit's stealth started to show its limits. The B&B Lancer was already struggling, with only half of its fleet operational by the early 2010s, and the B-2 wasn't immune to the pressure either. Advancing radar systems, multi-frequency detection, and data from satellites and drones began exposing weaknesses in its once undetectable design. What was once an invisible shield became a sophisticated cloak, still effective, but no longer perfect. This raised serious concerns for the United States Air Force Strategic Command. It was time to rethink the future of stealth bombers. By the 2010s, it is evident that not all bombers would continue serving the same role. The B-52, first introduced in the 1950s, kept getting upgrades, with plans to keep it flying for decades. At the same time, the B-1B was removed from the United States nuclear strike system. The B-2 was still a powerful machine, but its high cost, complexity, and aging stealth technology made it less reliable for large-scale missions. It was clear that the next-generation bomber had to be something new, stealthy, durable, adaptable, and free from the hefty price tag and maintenance challenges of the B-2. As warfare advanced, the need for a new bomber became urgent. Hypersonic missiles, space-based weapons, high-powered lasers, smarter air defenses, and artificial intelligence capable of learning enemy tactics were making older strategies obsolete. Technology was evolving fast, and for the United States to stay ahead, it needed a bomber built for the future. After years of development, that solution finally arrived: the B-21 Raider, designed to remain hidden and untouchable. The United States Air Force realized that just making another stealth bomber wouldn't cut it. The world was shifting rapidly, and the threats were evolving just as fast. They needed something completely different, a strategic bomber that could not only survive in current combat zones, but dominate whatever conflicts might emerge in the future. This vision became reality in 2011 when they launched the Long-Range Strike Bomber program. The goal was straightforward: create a next-generation intercontinental stealth aircraft that could handle anything. But this bomber would do much more than just drop conventional and nuclear weapons. The aircraft would serve multiple roles. It could gather critical intelligence behind enemy lines, coordinate complex battlefield operations across vast distances, intercept enemy aircraft when needed, and adapt to whatever new missions emerged around the globe. Essentially, they were building a flying command center that could strike, spy, and coordinate, all while staying completely invisible to enemy radar systems. The military understood that future conflicts wouldn't look like past wars. They needed an aircraft that could evolve with changing circumstances rather than one designed for a single specific threat. With goals that big, the Air Force had something specific in mind: a multi-role war machine they called a sixth-generation global precision strike platform. The idea was to merge stealth technology with advanced sensors and incredible range, giving military commanders the power to spot and hit threats from virtually anywhere on Earth. When it came time to choose a contractor, they selected Northrop Grumman. This was the same company that built the famous B-2 Spirit, so they knew their way around stealth bombers. But this time around, Northrop Grumman made a key promise: they would keep costs under control. The B-2 had been a public relations nightmare because of its enormous price tag. People couldn't believe how much each aircraft cost, and it created serious political problems for the program. Northrop Grumman understood they couldn't afford another financial disaster like that. This project wasn't just about creating an incredible piece of military hardware. It was also about developing cutting-edge technology. It was also about proving they could deliver cutting-edge performance without breaking the bank. The company needed to rebuild confidence in both its engineering capabilities and its financial management. Success meant delivering a bomber that worked brilliantly and cost what they said it would cost. The B-21 Raider might look a lot like the B-2 Spirit at first glance, but it's far from just an upgrade. When designing a stealth flying wing, engineers have two choices: stick with what works or take a risk on flashy new concepts that often fail in real combat. The Raider follows a proven design but pushes it further. It's closer to the original early blueprints of the Advanced Technology Bomber program than the final B-2. Unlike the Spirit's jagged trailing edges, the B-21 has a smoother, more refined shape, built for high-altitude missions and optimized to stay nearly invisible to radar from every angle. Flying at higher altitudes gives the Raider a significant edge, like standing on top of a mountain with a set of binoculars. From up there, visibility is unmatched, allowing it to detect and track things others might miss. The same principle applies to the B-21. Operating at higher elevations enhances its sensors and communication systems, making it easier to gather and share critical data. This isn't just about keeping the bomber safe. It's about giving nearby friendly forces a real-time, full-picture view of the battlefield, like a lookout scanning the entire sky from above. This capability becomes crucial on modern battlefields, where making the right decisions quickly often depends on having fast, reliable information. The B-21 is being built to work closely with other advanced aircraft, particularly the sixth-generation fighter jets that are part of the next-generation air dominance program. When these aircraft operate together, they form a connected network of platforms that can instantly share information. Instead of each plane working alone, they function as parts of a larger system. This approach enables them to coordinate attacks, share threat warnings, and respond to changing situations much faster than traditional aircraft operating independently. The focus isn't just on making individual aircraft stronger or faster. It's about creating a cohesive force that works together, adapting in real time based on shared intelligence across an entire network. The B-21's biggest advantage is its open architecture, meaning it was designed to evolve. As technology advances, whether it's hypersonic missiles, high-energy lasers, or next-generation artificial intelligence, the B-21 can be upgraded without needing a completely new design. That adaptability keeps it ahead of emerging threats for decades, unlike older bombers that became outdated due to rigid structures. In a rapidly changing battlefield, its ability to stay relevant makes it a lasting investment in American air power. One of the most significant upgrades is its extended range. The B-21 is designed to cover thousands of miles without needing to refuel, making it a game-changer for missions deep inside heavily defended territory. Today's adversaries are building advanced anti-access and area denial zones, so long-range endurance isn't just an advantage, it's essential. By flying higher, traveling farther, and operating smarter, the Raider isn't just built to survive in hostile airspace. It's built to dominate it. The B-21 Raider isn't just built for long flights. It's designed to stay airborne longer than any bomber before it. Current U.S. bombers already take on marathon missions lasting over 24 hours, but the B-21 is expected to extend that even further. A big reason for that is fuel. Even though it's about 2/3 the size of the B-2 Spirit, it has redesigned shorter internal weapons bays, which free up space for extra fuel storage. That added capacity, combined with a more compact, efficient layout, has even earned it the nickname stealth gas tank among some. Its fuel efficiency isn't just about storage. Unlike the B-2, which relies on 4 engines, the Raider runs on 2, a design choice that cuts fuel consumption without compromising performance. Northrop Grumman hasn't officially revealed which engines power the B-21, but this twin-engine setup plays a key role in maximizing efficiency. When a person combines that with its long-range capabilities and high-altitude flight profile, you get an aircraft built for extended missions, crossing oceans and continents without needing to refuel mid-flight. One of the B-21's most unique features is its recessed air intakes, carefully built into the bomber's body. This isn't just about looks, it's a crucial part of reducing radar visibility from almost every direction. Air intakes have always been a challenge in stealth aircraft design because they tend to disrupt the smooth surfaces needed to deflect radar waves. But on the radar, engineers have found a way to integrate them without compromising stealth, proving just how much technology has evolved since the B-2. It's a small detail with a significant impact on survival in contested airspace. Even though its sleek design might look like it limits its payload, the B-21 is built to carry serious firepower, especially for its most critical mission. A key goal of the Long-Range Strike Bomber program is to make sure the Raider can deliver advanced nuclear weapons deep into enemy territory. To do that, it's equipped with the stealth-capable AGM-181 long-range standoff cruise missile, designed to hit targets from far outside hostile defenses. In the end, the B-21 isn't just efficient, it's powerful, precise, and nearly impossible to detect. By December 2022, the United States Air Force had already run at least 9 test flights of its newest advanced missile system. Just 3 months later, in March of the following year, that missile cleared a critical design review, moving one step closer to being deployed with both the B-21 Raider and the B-52 Stratofortress fleets. But that's just part of the larger plan. According to Air Force Secretary Frank Kendall, the B-21 may carry more than just conventional or nuclear weapons. It could also be equipped with directed energy systems, including high-powered combat lasers currently being developed by Lockheed Martin. These next-generation weapons are part of a larger strategy shift. Alongside the B-21 Raider and the upcoming 6th-generation fighter jets from the Next Generation Air Dominance program, the Air Force is building what it calls a family of systems. A significant piece of this network will be collaborative combat aircraft, autonomous wingman drones powered by artificial intelligence. To develop these drones, the Air Force plans to invest nearly $9 billion between 2025 and 2029. The goal is to reduce the number of pilots needed and create squadrons where manned and unmanned aircraft work together seamlessly. Right now, flight testing has already started with the first B-21 prototype. Northrop Grumman has 5 more Raiders being built at various stages. Plus, they're also constructing some non-flying versions just for ground testing purposes. The plan is ambitious. They want at least 100 B-21 Raiders ready by the early 2030s. When considering the complete program over the next 30 years, encompassing all research, building, and maintaining these planes, the total cost exceeds $203 billion. Even with that massive overall price tag, each B-21 should cost around $700 million. That might sound like a lot, but it's a considerable improvement over the B-2 Spirit, which ended up costing over $2 billion for each aircraft. This dramatic cost reduction demonstrates that Northrop Grumman has learned valuable lessons from the B-2 program. They figured out how to build advanced stealth bombers without the financial disasters that plagued earlier projects. Getting more capability for less money means the military can afford to buy enough of these aircraft to make a real difference. With that level of investment, there's a lot on the line. Can the United States Air Force pull off a thoroughly modern bomber fleet by 2030 while also rolling out 6th-generation fighters and autonomous drones? One thing is clear, the next few years will shape the future of air dominance, and the battle for the lead is already underway.
At 2:17 a.m. local time over the Red Sea, a radar warning blared in the cockpit of America's most advanced stealth bomber. January 12, 2024. What began as a routine mission suddenly became a high-stakes combat encounter as multiple heat signatures streaked toward the $2 billion aircraft. In the darkness above international waters off Yemen's coast, Houthi rebels had just attempted the unthinkable, to shoot down the world's stealthiest plane. But how do you hit what you can't see? And what happens when you target the wrong stealth bomber? The first indication of trouble came from specialized sensors aboard the B-2 Spirit. Flying at 45,000 feet in the dark skies over the Red Sea, the bomber's defensive systems detected multiple missile launches from positions along Yemen's western coastline. Within seconds, the aircraft's threat warning system identified the incoming projectiles as modified R-27 surface-to-air missiles, weapons that shouldn't have been in Houthi hands at all. At that same moment, radar operators aboard the USS Dwight D. Eisenhower Carrier Strike Group detected a swarm of unidentified aerial vehicles rising from Houthi-controlled territory. The drones moved in a coordinated pattern, clearly targeting the airspace where American aircraft were operating. This wasn't a random attack. It was a deliberate, coordinated attempt to bring down one of America's most valuable military assets. The B-2's two-person crew immediately executed their defensive protocols. While the pilot initiated evasive maneuvers, the mission commander activated the aircraft's suite of electronic countermeasures. What followed was a high-tech battle of technological cat and mouse that would test the limits of American stealth technology against increasingly sophisticated non-state actors. The B-2 Spirit represents the pinnacle of American stealth technology. This flying wing, with its distinctive bat-like silhouette, revolutionized aerial warfare when it first flew in 1989. What makes the B-2 special is its ability to penetrate the most sophisticated air defense systems undetected, deliver precision strikes, and return home safely. Cost: $2.1 billion per aircraft. Range: 6,900 miles without refueling. Payload: 40,000 pounds of conventional or nuclear weapons. Fleet size: just 20 aircraft in existence. The bomber's stealth capability comes from its unique shape, special radar-absorbing materials, and hidden engine exhausts that minimize both radar and heat signatures. For more than 3 decades, the B-2 has been America's ultimate penetrating bomber, capable of striking anywhere on Earth with near impunity. The Houthi movement, formerly known as Ansar Allah, supporters of God, emerged from Yemen's northern highlands in the 1990s. What began as a Zaydi Shia religious revival transformed over decades into a powerful armed faction that now controls much of western Yemen, including the capital city of Sana'a. Since 2014, the Houthis have been locked in a brutal civil war against Yemen's internationally recognized government, which is supported by a Saudi-led coalition. This conflict has created one of the world's worst humanitarian crises, with millions facing starvation and disease. The Houthis receive significant support from Iran, which provides weapons, training, and technical expertise. Their official slogan, "God is great, death to America, death to Israel, curse on the Jews, victory to Islam," clearly establishes their ideological opposition to the United States and its allies. In recent months, the Houthis have escalated their campaign against international shipping in the Red Sea, claiming solidarity with Hamas in the ongoing Gaza conflict. This campaign has disrupted global trade routes and prompted an international naval response. The attack on January 12, 2024 represented a significant escalation, directly targeting American military aircraft operating over international waters approximately 30 miles off Yemen's western coast. The most puzzling aspect of this incident is how the Houthis could have detected a stealth bomber specifically designed to evade the world's most sophisticated air defense systems. 3 distinct theories have emerged. Theory A: state-backed detection. Iran, which actively supports the Houthis, has invested heavily in counter-stealth radar technology. These systems, potentially including Russian-designed low-frequency radars, can sometimes detect the general presence of stealth aircraft, though with less precision than would typically be needed for targeting. Intelligence reports suggest Iranian technical advisors may have been operating these systems from positions within Yemen. Theory B: thermal detection. Even the stealthiest aircraft still produce heat. Advanced infrared search and track (IRST) systems can potentially detect a B-2's engine exhaust or the friction-heated leading edges of its wings, especially when viewed from certain angles. The Houthis may have acquired sophisticated IRST systems through their Iranian connections. Theory C: intelligence network. The most concerning possibility involves neither radar nor infrared detection, but human intelligence. The Houthis might have received advance information about the B-2's deployment through espionage networks monitoring U.S. bases in the region. Alternatively, they could have pieced together clues from open-source intelligence like aircraft spotters or satellite imagery showing support activities. Analysis from defense experts suggests the most probable explanation combines elements of theories A and C. The Houthis likely had advanced intelligence about U.S. air operations in the region and used Iranian-supplied low-frequency radar to detect an aircraft entering their sensor coverage. However, the precision of their targeting suggests they mistook the specific aircraft type, a crucial error that would ultimately save the B-2. What exactly does it mean that the Houthis targeted the wrong B-2? Three possibilities explain this intriguing aspect of the incident. The Houthis may have detected a large American aircraft but misidentified its type. While the B-2's distinctive shape is unlike any other aircraft, limited radar returns or partial infrared signatures could have been misinterpreted. They might have believed they were targeting a B-2 when they were actually tracking a different aircraft entirely, such as a B-1B Lancer bomber or even a large reconnaissance aircraft. More sophisticated explanation involves deliberate deception by U.S. forces. Electronic warfare aircraft like the EA-18G Growler can generate false radar returns mimicking other aircraft. In this scenario, U.S. planners may have created electronic decoys appearing to be B-2 bombers specifically to lure out and identify Houthi air defenses, a classic wild weasel tactic updated for the stealth era. The Houthis may have correctly identified a B-2 but failed to recognize the strategic significance of attacking such a high-value American asset. In this scenario, they targeted the wrong B-2, not in terms of aircraft identification, but in terms of strategic calculation, choosing a target that would inevitably provoke a severe American response beyond what they anticipated. Intelligence assessments lean toward the decoy operation theory. The precision of the Houthi targeting suggests they genuinely believed they were engaging a B-2, but post-incident analysis reveals no actual B-2 was in the exact location targeted. This points to a sophisticated electronic deception operation designed to map Houthi air defense capabilities while keeping actual high-value assets at safe distances. At 2:17 a.m., multiple R-27 missiles launched from mobile platforms near Yemen's western coast. Originally designed as Soviet air-to-air missiles, these weapons had been modified for surface-to-air use, a technical achievement requiring considerable expertise. The missiles accelerated to over Mach 2.5, climbing rapidly toward their target altitude of approximately 45,000 feet. The targeted aircraft immediately deployed a sophisticated array of defensive systems. Electronic jammers broadcast signals designed to confuse the missile's guidance systems, while flare dispensers ejected high-temperature decoys to draw away any infrared-guided weapons. The aircraft executed a series of subtle course and altitude changes, enough to complicate targeting without compromising its stealth characteristics. FA-18. Super Hornets from the USS Eisenhower, flying combat air patrol nearby, immediately targeted the missile launch sites. Using targeting data shared through secure networks, the fighters launched precision munitions at the mobile launchers. Simultaneously, the carrier's electronic warfare aircraft began jamming Houthi command and control frequencies, disrupting their ability to coordinate the drone swarm that formed the second wave of the attack. Within 4 minutes of the initial missile launch, U.S. forces had neutralized the immediate threat and begun a counteroffensive against the Houthi air defense network. Not a single missile reached its intended target. As the missile attack unfolded, a second threat emerged from Houthi territory. Approximately 24 small unmanned aerial vehicles rose from multiple launch sites, forming a coordinated swarm pattern. These weren't crude commercial drones, but purpose-built attack platforms with shaped explosive charges, specifically designed to damage aircraft. The drone swarm represented an evolution in Houthi capabilities. By using multiple simple platforms attacking simultaneously from different directions, they hoped to overwhelm traditional defenses. Even if individual drones lacked sophisticated guidance, the sheer number created a statistical probability of successful strikes. American forces countered this threat using multiple systems. Navy EA-18G Growlers deployed electronic warfare techniques to sever the command links between the drones and their operators. When this proved only partially successful against autonomous drones, laser-based counter-drone systems aboard accompanying aircraft disabled several more by overheating their control systems. The remaining drones were engaged by close-in weapon systems from naval vessels and defensive fire from patrolling fighters. The multi-layered defense proved effective, but the sophistication of the swarm attack surprised many military analysts. It demonstrated a level of tactical coordination previously unseen in Houthi operations. Within hours of the failed attack, the U.S. military launched a coordinated response against Houthi military infrastructure. The operation, codenamed Decisive Shield, involved 38 precision strike missions against air defense installations, 12 cruise missile launches targeting underground command bunkers, coordinated cyber operations disrupting Houthi communications networks. Unlike previous limited strikes against Houthi launch facilities, this operation specifically targeted the group's strategic military infrastructure. Precision-guided munitions struck radar installations, missile storage facilities, and command and control centers across Pentagon. Officials confirmed that the strikes employed both sea-launched Tomahawk cruise missiles and air-delivered munitions from carrier-based aircraft. Satellite imagery released 48 hours after the operation showed extensive damage to multiple Houthi military facilities, particularly their air defense network. The speed and scale of the American response sent a clear message. Attacks on high-value U.S. military assets would trigger disproportionate consequences. Defense analysts noted this represented a significant escalation in the U.S. posture toward Houthi forces, moving from limited retaliation against specific launch sites to broader strikes against military infrastructure. The failed attack and subsequent American response triggered a cascade of strategic consequences throughout the region. Within days, satellite imagery showed Iranian naval vessels that had been operating near Yemen's coast withdrawing to safer waters. Intelligence sources reported heightened communications between Iranian advisors and Houthi leadership, suggesting serious reassessment of their tactics. For U.S. military planners, the incident prompted immediate changes to operational security around high-value air assets. Flight patterns, electronic emissions, and support operations for stealth aircraft received enhanced protection measures. Sources within the Pentagon indicated that deployment protocols for B-2 bombers would undergo comprehensive review before future missions to the region. The most significant long-term impact may be on the perception of stealth technology's vulnerabilities. While no actual B-2 was damaged in the incident, the apparent ability of a non-state actor to detect and target what should have been an invisible aircraft raised serious questions. Defense contractors working on next-generation platforms like the B-21 Raider reportedly accelerated development of enhanced counter-detection systems in direct response to the incident. Regional allies quickly aligned behind the American response. Saudi Arabia and the United Arab Emirates offered additional intelligence support for operations against Houthi air defenses. Israel, concerned about similar capabilities potentially reaching Hamas or Hezbollah, reportedly shared specialized electronic warfare techniques specifically designed to counter the types of detection systems used in the attack. The B-2's stealth technology was designed in the 1980s to defeat Soviet-era radar systems. Its shape scatters radar energy away from receivers, while special materials absorb remaining signals. However, as with all military technology, countermeasures have evolved in parallel. Modern anti-stealth systems approach detection from multiple angles. Low-frequency radars can detect stealth aircraft but lack precision for targeting. Infrared search systems look for engine heat rather than radar returns. Passive detection systems identify when normal background radiation is blocked. Networked sensors combine multiple weak detections into actionable intelligence. Future stealth aircraft like the B-21 Raider incorporate lessons from these evolving threats. More comprehensive radar-absorbing materials effective across broader frequency ranges. Advanced cooling systems that further reduce infrared signatures. Active countermeasures that can jam or deceive incoming sensors. Operational tactics that minimize exposure to known detection methods. The incident demonstrates the fundamental truth about stealth technology. It's not invisibility, but rather a significant reduction in detectability that creates tactical advantages. As detection technology advances, stealth designs must evolve in response. World powers responded to the incident based largely on their strategic interest in the region and relationship with the involved parties. Russia and China paid particular attention to the technical aspects of the engagement. Chinese military publications produced detailed analyses of potential B-2 vulnerabilities exposed by the incident, while Russian state media emphasized the growing sophistication of counter-stealth technologies. Both nations have invested heavily in detecting American stealth platforms, and this real-world test provided valuable insights despite the attack's failure. Saudi Arabia and other Gulf Cooperation Council members publicly supported the American response, seeing it as reinforcing deterrence against Iranian-backed groups throughout the region. Kuwait and Bahrain offered expanded access to military facilities for U.S. forces involved in follow-up operations. These nations, which have faced their own Houthi attacks, welcomed the more forceful American posture. The United Nations Security Council convened an emergency session, but failed to produce a unified statement due to Russian and Chinese objections to language condemning the Houthi attack. Iran officially denied involvement, but quietly opened back-channel communications with American representatives through Omani intermediaries, seeking to prevent further escalation that might directly implicate Iranian forces. European allies expressed concern about the potential disruption to maritime commerce, but generally supported the measured American military response. NATO Secretary General Jens Stoltenberg characterized the incident as a dangerous escalation by non-state actors possessing increasingly sophisticated weapon systems. The failed attack revealed three critical insights that are reshaping military thinking about aerial operations in contested environments. The incident confirms what military planners have long suspected: no aircraft is completely undetectable against all sensor types. Future operations must assume at least partial detection capability by adversaries, even those without state-level resources. This doesn't make stealth obsolete, but changes how it's employed tactically. The coordinated drone attack represents a new paradigm in asymmetric warfare. Large numbers of relatively simple platforms can create complex defensive challenges even for sophisticated military forces. Countering such swarms requires multi-layered defenses combining electronic warfare, kinetic interceptors, and directed energy weapons. The technical sophistication shown by the Houthis, combining multiple detection methods, missile systems, and drone swarms, demonstrates how advanced air defense capabilities are spreading beyond state actors. This trend will reshape how air campaigns are planned and executed in future conflicts. Military analysts point to these lessons as accelerating existing trends in air warfare development. The U.S. Air Force's Next Generation Air Dominance program, which will complement the B-21 Raider bomber, reportedly shifted some development priorities toward enhanced counter-detection capabilities in direct response to the incident. Behind the technology and tactics lies the human dimension of the incident. The B-2 crew's rapid response to incoming threats demonstrated the exceptional training that stealth bomber pilots undergo. Their ability to maintain the aircraft's stealth profile while executing defensive maneuvers represents a pinnacle of aviation skill. Similarly, the command decisions to launch an immediate and substantial retaliatory strike reflect evolving American strategic thinking about deterrence. The calculated escalation, striking military infrastructure rather than just launch sites, showed a willingness to impose costs that outweigh any potential benefits Houthi forces might gain from attacking high-value U.S. assets. On the Houthi side, the attack revealed both technical sophistication and strategic miscalculation. The technical capability to coordinate complex, multi-domain attacks suggests significant external support and training. However, the decision to target or appear to target a B-2 bomber reflects either overconfidence in their capabilities or a fundamental misunderstanding of likely American responses. This human dimension, the calculation of risks, costs, and benefits under pressure, ultimately determines how technological capabilities are employed. In this case, American forces demonstrated superior decision-making that maximized their technological advantages and minimized vulnerabilities. 6 months after the incident, several enduring consequences have emerged. The U.S. military has adjusted its force posture in the region, maintaining a continuous presence of air defense specialists and electronic warfare assets. Stealth aircraft deployments continue, but with enhanced security measures and different operational patterns. Houthi forces have largely refrained from directly targeting American military assets, focusing instead on commercial shipping, suggesting they recognize the attack crossed a threshold that brought disproportionate response. Their air defense network, severely degraded by American strikes, has only partially recovered. The technological insights gained from the incident have accelerated defense programs in multiple countries. Counter-drone systems, passive detection networks, and advanced electronic warfare capabilities have received increased funding across NATO allies. Perhaps most significantly, the successful defense against what should have been an impossible detection has reinforced a core military truth. Technological advantages are always temporary. The continuous cycle of measure and countermeasure ensures that today's revolutionary capability becomes tomorrow's vulnerable legacy system. Recently declassified intelligence has transformed our understanding of the January 12th incident. Pentagon sources now confirm the Houthi attack employed a complex three-layered air defense strategy far exceeding initial assessments. Satellite imagery shows the rebels activated 3 separate air defense clusters along Yemen's western coastline in a carefully orchestrated sequence, creating overlapping detection zones specifically designed to catch even low observable aircraft. The pattern wasn't random or opportunistic. Analysis of radar activation timestamps shows a sophisticated trap configuration. Primary radars remained mostly dormant until secondary passive sensors detected potential targets, at which point the entire network activated in a synchronized pattern lasting just 94 seconds. This brief activation window minimized detection risk while maximizing coverage effectiveness. Such operational discipline represents a significant evolution in Houthi air defense tactics previously considered well beyond their indigenous capabilities. Most concerning to Western intelligence agencies was the precision timing of the engagement sequence. The Houthis employed a disciplined emissions control protocol, keeping their radar systems inactive until the critical moment, then coordinating near-simultaneous missile launches from geographically separated locations. This approach demonstrated both technical expertise and tactical sophistication typically associated with state-level military operations, not non-state actors. Despite continued official denials, forensic evidence now conclusively links Iran to the attack hardware. Analysis of missile fragments recovered by Navy SEAL teams in a classified operation 3 days after the incident revealed components manufactured as recently as October 2023. The guidance systems contain specialized microelectronics traced to facilities associated with Iran's Revolutionary Guard Corps Aerospace Division, not repurposed Cold War technology as initially suspected. Technical analysis of the radar emissions captured during the attack revealed frequency hopping patterns and encryption protocols identical to those documented in Iranian air defense exercises conducted last September. The specific electronic signatures match those from Iran's Khordad air defense system, suggesting either direct technology transfer or on-site operation by Iranian specialists. Most alarming to Pentagon analysts was the discovery that the missiles employed advanced counter-digital systems designed specifically to penetrate Western electronic warfare protections. The countermeasures appeared calibrated against specific American jamming techniques, suggesting Iranian defense engineers had been systematically studying and adapting to U.S. electronic warfare capabilities, possibly through data collected during previous Gulf encounters. Military officials have now confirmed the wrong B-2 theory that circulated in defense circles. The operation centered on a sophisticated electronic deception campaign designed to map Houthi air defense capabilities while protecting actual high-value assets. An EA-18G Growler electronic warfare aircraft projected carefully crafted electromagnetic signatures mimicking those of a B-2 bomber while flying a completely different flight path. The deception employed the Navy's next-generation jammer midband NGJMB system, creating what appeared on Houthi radars as a stealth bomber penetrating Yemeni airspace, while the actual Growler remained in international airspace following a separate trajectory. This electronic phantom triggered exactly the response U.S. intelligence sought: full activation of the Houthi air defense network, revealing its composition, capabilities, and command protocols. The operation succeeded brilliantly, but at considerable risk, as the Growler deliberately made itself detectable to map the full extent of Houthi radar coverage. Post-incident analysis revealed one missile detonated approximately 2,300 feet from the American aircraft, significantly closer than previously acknowledged in public briefings. The actual B-2 bombers operating in the region remained completely undetected throughout the engagement, conducting their mission profile at a safe distance while the electronic deception operation unfolded. This validation of the B-2's continued effectiveness against emerging threats has reinforced Air Force confidence in the platform despite its aging technology baseline. Technical analysis of recovered drone fragments has substantially revised initial assessments of Houthi unmanned capabilities. Far from simple commercial drones with explosive payloads, the captured specimens revealed sophisticated military-grade systems with multiple specialized variants. The most numerous type carried conventional explosive warheads with advanced proximity fuses designed to detonate near aircraft without requiring direct impact. However, intelligence officials were startled to discover 4 specialized electronic warfare variants among the wreckage. These units carried no explosives, but instead housed compact jamming systems targeting specific frequency bands used by American aircraft for navigation and communication. Forensic analysis of the drone flight control systems revealed sophisticated autonomous target recognition capabilities. The onboard processors contain machine learning algorithms trained to distinguish between aircraft types using infrared and visual signatures, with specific parameters focused on American aircraft, including FA-18 Super Hornets and support aircraft. This level of targeting sophistication strongly suggests access to advanced technical data and training resources typically controlled by state-level military organizations. Recently declassified operational reports reveal the electronic countermeasures employed against the Houthi attack were far more extensive than initially disclosed. Beyond traditional defensive systems, the operation involved a coordinated electronic warfare campaign across multiple platforms and domains. The targeted EA-18G Growler aircraft deployed the AN/ALQ-249 next-generation jammer in one of its first combat operations since achieving initial capability. This system simultaneously generated false targets across multiple radar bands, jammed missile guidance frequencies, and disrupted Houthi command networks using precisely directed high-power microwave energy. Supporting Navy vessels contributed additional electronic warfare coverage, creating a multi-layered defensive electronic bubble. Particularly effective was a classified technique called ghost returns that created multiple false targets with flight characteristics mimicking the actual aircraft. This technique fragmented the Houthi targeting solution, forcing their systems to track multiple phantom signatures simultaneously. When missiles launched, these false signatures attracted several weapons that detonated harmlessly miles from any actual aircraft. Space-based assets played a previously undisclosed role in the defensive operation. Classified electromagnetic monitoring satellites provided real-time tracking of Houthi radar emissions, allowing immediate characterization and jamming of threat frequencies. This orbital support enabled American electronic warfare officers to precisely target countermeasures against specific emitters, effectively neutralizing the integrated air defense network without requiring kinetic strikes against each installation. The failed Houthi attempt to target a B-2 stealth bomber, or what they believed was one, demonstrates both the enduring value of stealth technology and its evolving limitations. Despite advances in detection systems and their proliferation to non-state actors, properly employed stealth aircraft remain extraordinarily difficult to target effectively. The incident reveals the central paradox of modern air warfare. Absolute invisibility is impossible, but significant reduction in detectability continues to provide decisive military advantages. The B-2, even as a mature platform nearing retirement, demonstrated resilience against a sophisticated multi-domain attack. For military planners worldwide, the key lesson is clear. Stealth isn't invulnerability. It requires supporting tactics, electronic countermeasures, and intelligent employment to remain effective. As non-state actors continue leveling up their capabilities, the technological race between detection and evasion accelerates. Next time, the question won't be whether the aging B-2 can survive such encounters, but whether its successor, the B-21 Raider, has incorporated the right lessons from this incident to maintain America's edge in the increasingly contested skies of tomorrow's conflicts. The invisible war between stealth and detection continues, with each side claiming temporary advantages in an endless cycle of technological evolution. Thanks for watching another episode. While you are still here, make sure to click on the video on your screen for more quality content.